The program for today, the first speaker is Professor Nils Olsen, exploring the Earth's magnetic field using satellites from Østed to Schwarm. And Nils.
So thank you for that. In this talk, exploring the Earth's magnetic field from space, I will try to convince you that if we combine state-of-the-art technology of how to measure the Earth's magnetic field and novel approaches how to separate the different sources, then we can really find out what's going on inside of our planet. The outline of my talk is the following. First, we will look at the data, the observations, and the different sources that contribute to these observations. In the next part, we'll look at methods, how can we separate these different source contributions. Third part is how we can use these geomagnetic field model that we estimate from the data. What do they tell us about processes in the Earth's interior? And then finally, a look into the future, the near future, which already has started, the Swarm satellite constellation that was launched in November last year. So let's start with the introduction, with the observations. Satellites for measuring the Earth's magnetic field, we have had that for almost 50 years. It started with the POGO satellite series that flew for a few years, but they only measured the magnetic field intensity. The first vector mission was the MAXAT mission. It flew only for 6 months. And after MAXAT, there was a gap of almost 20 years until February 1999 with the launch of the Danish Ørsted satellite. And since then, we have continuous or almost continuous measurements from space. Ørsted, then 1 year later, we had the launch of the German SEM satellite and the Argentinian SAC satellite. And then, in November last year, the launch of the 3-satellite constellation Swarm, consisting of, 3 satellites. All these recent satellites and also Swarm, they carry essentially the same instrumentation. So what do these satellites measure? Well, first of all, why do we want to measure Earth's magnetic field from space? The key word here is global coverage. On the left-hand side, you see a map, and these red dots represent the location of the ground-based observatories. These are sites that monitor hour by hour, minute by minute, second by second, how the Earth's magnetic field changes. We have about 150 observatories, but as you can see, there are huge gaps, especially in the oceans. If we take 1 day worth of satellite data, we get a global coverage which is much better. And we have this typical pattern. The reason for this pattern is the following. We have the orbital plane of the satellite. And this orbital plane is fixed or almost fixed with respect to the sun, but the Earth is rotating underneath that. So 1 rotation within 24 hours. 1 satellite orbit takes about 90 minutes, which means we have 15 orbits per day. And the ground track of these 15 orbits, that's shown here. This is the global coverage with 1 day worth of data. With 3 days, we have this. And now you can imagine we collect data for months and years. So we get a really good global coverage, which allows us to study not only the small-scale structure of the field, but also how the magnetic field evolves with time. So what does a satellite measure as a magnetic field? Well, the different contributions. We have the interaction of the solar wind with the Earth's magnetic field. This gives some electric currents in the ionosphere and in the magnetosphere. These are the so-called external sources. And then we have the internal sources. This is magnetized material in the crust. The mantle is non-magnetic, however, we have secondary induced currents. And then finally we have the fluid motion in the outer core. This gives the core field. So to summarize, the internal sources, we have magnetized material in the crust, with the mantle essentially non-magnetic, and then we have the movement of molten iron in the outer core. So let's look at the order of magnitude of these different sources. The internal sources, that's the core field. About 94% of the observed field at the Earth's surface is due to the core. The crustal field is comparably weak, so only 3% on average, but locally it's much stronger. So core and crustal field are the internal sources, and then in addition to that we have the external sources. Current systems in the ionosphere and in the magnetosphere. They are weak on average, but it's very essential that we consider these external sources, even if we are only interested in studying the core and crustal field. Otherwise, if we do not consider them, we will get a biased model of the core and crust. Let's now have a slightly different look at these different sources. What you see here is the radial magnetic field component at a satellite altitude, at an altitude of 400 kilometers. This figure is rather boring. So we have red color, which means positive radial component in the southern hemisphere, a negative radial component in the northern hemisphere. Of course, that means you have field lines emerging from the southern hemisphere and into the northern hemisphere. The scale is plus minus 60,000 nanotesla. Here in London, we have presently about 50,000 nanotesla. That's the field strength presently here. Okay, this is now an animation. Let's start that. What we will do is we will remove one source after the other and then look at what's remaining. So I have to start this. So the Earth is rotating, still dominated by the core field. Then we remove the core field. What's left over is almost nothing. But then we have to increase the sensitivity by a factor of 1,000. Now the scale is plus minus 60 nanotesla. And what you see now is a magnetospheric storm. So that's dominated by the magnetospheric field now. If you also remove the magnetospheric field, what's now left over is dominated by the ionospheric field, especially on the day side. The night side is calm, but on the day side we have the movement of a current system with the sun. Finally, if we also remove the ionospheric field, what's left over is now dominated by the crustal field, about 10 kilometers at satellite altitude, 10 nanotesla at satellite altitude. And finally, if we also remove the crustal field, and then we really have to increase sensitivity, what we see now here is a tiny magnetic field. That's the magnetic field due to the tidal motion of the conducting seawater. So plus minus 2 nanotesla to plus minus 60,000 nanotesla. That's the order of magnitude that we have to consider here. So let's now move on. How can we separate these different sources? The main tool that we have is the geomagnetic field modeling. So what we do here is the following. We assume the magnetic field is a potential field, so it can be derived by a potential V, which is then expanded into a series of spherical harmonics. We have coefficients G and M and H and M describing the internal sources, and coefficients Q and M, SMN, shown in blue, describing the external sources. By taking measurements of the vector field, it is possible to separate external and internal sources. One attempt to do that is the Chaos-4 model. The goal is to have a model that describes small-scale features of the field, so the spatially small-scale feature of the core and crustal field, but also to see rapid core field changes. And the way we do that is it's rather sophisticated. It's based on almost 15 years of data from all these 3 satellites, Earth, Champ, and Saxi, in combination with data from 150 ground-based observatories. The model parameterization, well, we use spherical harmonics, but also we have a rather complicated, sophisticated co-estimation of external field and of the instrument calibration parameters. In total, we estimate about 25,000 parameters based on about 1.5 million observation points. Okay, and once we have these Gauss coefficients, these expansion coefficients, G and N and H and M, of the internal field, we can calculate a quantity that's called the geomagnetic spectrum. We take these coefficients, G and M, H and M, square them up, and then we sum them for one specific degree n and for all orders. And this is then this quantity called Rn. That's a concept that has been introduced almost 50 years ago by Frank Lowes, and it has a physical meaning. It is the mean square magnetic field at the Earth's surface due to contributions with a certain horizontal wavelength. And this wavelength is given by this equation. So let's start with an example. We take the dipole. Dipole means n equal to 1. The horizontal wavelength of a dipole is just the circumference of the Earth. It's 40,000 kilometers. So n equal to 1 corresponds to 40,000 kilometers. If you take n equal to 10, this corresponds to a wavelength of 4,000 kilometers and so on. So the higher the degree, the smaller the spatial scale that we can describe. If you now take these Gauss coefficients and plot the spectrum, then we see something that is very specific, very typical for Earth. That's this sharp decrease in amplitude, and then suddenly the spectrum gets flat. The reason for this is the following. That's the core field, which is dominated up to spherical harmonic degree 13, and above that, it's dominated by the crust. And you can also see that a theoretical spectrum based on 4 parameters fits very well to these observations. So let's now look at what can these field models tell us about processes in the Earth's core. And here I just want to give 2 examples. The first example is how the Earth magnetic field changed during the last 15 years. This is the second time derivative of the Earth's magnetic field at surface. And you can see how dynamic the field is. These are processes, or this is caused by processes in the Earth's core. And that also means we can use these observations to infer what's going on in the core. Why can we do that? Well, the nice thing with the magnetic field is that it is a potential field. That means we are not only able to separate what are external sources and what are external sources and what are internal sources, but we can also make an upward-downward continuation. That means from observations at satellite altitude, we can infer what's the magnetic field at the Earth's surface and what's the magnetic field at the core mantle boundary. At least in principle, we can do that. The radial component at the Earth's surface is shown in the upper plot. If you make a downward projection to the core surface, then we get this picture here. So we see more small-scale structure because we are closer to the sources, and the scale here is plus minus 600,000 nanotesla. So the field is 10 times stronger at the top of the Earth's core compared to the Earth's surface. And the physics behind that is the following. That's the induction equation, which tells us that the first time derivative of the magnetic field is given by 2 terms, an advection term and a dissipation term. If you plug in typical numbers, then it turns out that the dissipation term is much, much smaller compared to the advection term. So we end up with the induction equation in the frozen flux approximation. That means the field lines, the magnetic field lines, are frozen into the material. We can use the field lines as tracer to find out how the material in the Earth's core is moving. At least in principle, we can do that. So that means from observations of B and B dot, we can infer the horizontal velocity. This problem is non-unique. You have to make additional assumptions. Here, one assumption is made, and that's the mean velocity for over the last 15 years. You can see that a typical velocity is about 20, 30 kilometers or so on. And this is actually the velocity at the at a depth of 3,000 kilometers. So that's the only way, the magnetic field is the only way to infer from observations what the fluid motion at the top of the Earth's core is. So this is about the core field. Let's now just move on to the crustal field. The crustal field based on the chaos 4 model. Well, you can see there are a lot of structures, and in particular, the crustal field is weaker in the oceanic regions compared to the continental regions. That's mainly because the continental crust is thicker compared to the oceanic crust. So let's now just move on to the more exciting stuff now, the next satellite mission, SWARM. So, SWARM. Well, SWARM is an ESA mission. It has been selected by ESA almost 10 years ago in 2004. And the launch was in November last year. SWARM is a constellation consisting of 3 satellites. 2 of them are flying side by side, and then we have a third satellite at a higher altitude. Here, what you see here is one of, this is the higher satellite. And shortly you will see the 2 lower satellites flying almost side by side. Here they are. So each of these 3 satellites measure the magnetic field with very high absolute accuracy, but also we measure the electric field, plasma density, and acceleration, and so on. So what's now the status of SWARM? Well, first of all, why are we interested in 3 satellites? And why are we interested in a constellation of 3 satellites? What is completely new with SWARM is that we have these 2 satellites flying side by side. They measure for the first time ever not only the magnetic field, but the east-west gradient of the magnetic field. And that contains valuable information about small-scale structure. What you see here is what one satellite would see. So this is the regular magnetic field due to the crustal. What is shown here on the right-hand side is the difference seen by these 2 side-by-side flying satellites. So that's the east-west gradient of the magnetic field. And you can see there's an enhancement of small-scale structure. That means we expect with SWARM that we will be able to see small-scale structure of the field that we can't see if we only have one satellite. And let's now illustrate that. This is a map of the crustal field based on very old satellite data. So this is Pogo and Maxot. This has a spatial resolution of 1,000 kilometers, so it's a spherical harmonic expansion up to degree in order 40. With the present satellites, Earth and Sham, we have a spatial resolution of 500 kilometers. What we expect with SWARM, based on a mission simulation that we have performed, is that we can see structures up to perhaps spherical harmonic degree 150, and corresponding to a spatial resolution of 270 kilometers. So what's now the status of SWARM? Well, we had a 3-month commissioning phase. This has been finished this year. There has been this week, sorry. You can see there has been some orbital maneuvers. They are not completed. The satellites are not yet at their final positions. But the first data have been released to the Calval team, and we expect perhaps some first scientific results at the EGU meeting in Vienna, and perhaps at the next International SWARM Science meeting in June. But let's look at an attempt what we have done during these first 3 months. That's shown here. So we took these first 3 months of SWARM data and estimated a field model up to spherical harmonic degree 40. And the spectrum of that field model is shown here with green color. And in red color is shown chaos 4. So we would expect that they are identical, at least for, or that they are the same, at least for the Crustal field, which is static. In black is shown the spectrum of the difference of these two models. So this is an indicator of the error. And you can see that the error for all degrees is below the signal. So that's a good sign. We would expect that the Crustal field, that means this part of the spectrum, is the same because the Crustal field doesn't change. So let's look at that. That's a map of the difference of this swarm-only model and chaos 4. And indeed, there's not much difference. So that's a good sign. And then let's look at the core field. Well, the core field, there are significant differences. These differences is due to the extrapolation error of chaos, because for chaos we have used old satellite data. The last satellite data that we have included are from June last year. But in order to compare with swarm, we have to make an extrapolation to now. And this is, of course, always dangerous. So this is the error that we made in chaos. And then finally, if I combine all available satellite data, Ørsted, CHAMP, SAXI, and swarm, then I make a correction for that. This is now an attempt to make chaos 4 plus, and then we get rid of these features. So that's just a glimpse of what the present situation is for swarm. And my conclusions, well, the future is very bright, at least for the next 10 years or so, where we expect many exciting results from the swarm satellite. Thank you.
Right, thank you. Questions?
I noticed there were two strong peaks in the Crustal field, one in Africa and one north of the Black Sea. Would you like to comment on the nature of those? What's their origin?
Well, we have actually three. One is in northern Sweden, and that's where I know what it is. That's iron. The other two, that's speculation. I don't know the answer, but perhaps others know it.
You mentioned measuring the electric field. Now, GPS system actually has that effect because although the satellites are 2,000 kilometers up and yours are only going to be 500 or 600 or so, as I understand from the graph you had, you're still going, the GPS system in effect monitors the status of the affair because the signals have to be corrected from what it's done to the signals. And therefore, in effect, there's a record of how the ionosphere is ahead. Now, are you going to be able to compare that record with what you get?
Yes, although here I would say what we measure, the electric field, that's an in situ measurement. What is affecting the GPS measurements is not so much the in situ electric field, but the total electron contents between these two. And we also measure that. Well, we measure that because we have GPS measurements.
Okay, right at the back there.
Is there a unique way to separate the various components of the field?
Yes, in a mathematical sense. But that requires that you have simultaneous measurements everywhere on the globe. And of course, even with 3 satellites, we don't have that. So we have to make some assumptions about stationarity of the field. Then we can separate external and internal fields. But also there is the issue. For instance, the satellites are flying above the ionosphere. So that means the ionosphere source is seen as internal by satellite, but they are external as seen by ground data. That's a challenge but it's also an opportunity. But there's no way to separate core and crustal field because they are inter. In order to separate core and crustal field, what we need is measurements in the mantle. The satellite in the mantle.
So I might have to wait for that. Okay. I think you've reduced them to silence.